Hello, good morning, students. Good morning, all of you. Good morning. I am Abdul Haq. Today, I am your physics teacher. So, today I want to teach about the chapter System of Particles and Rotational Motion. Rotational motion. In this, I want to explain torque and angular momentum. Okay, students. Okay, shall we start? Shall we start, students? Okay. Torque and angular momentum. So, what is torque? What is torque? In this section, we shall acquaint ourselves with two physical quantities which are defined as the vector products of two vectors that we shall especially amount in discussion of motion, system of particles, particularly rigid bodies. Moment of force, torque. Okay. We have learned that motion of a rigid body in general is a combination of rotation and translation. If the body is fixed at a point or along a line, it has only rotational motion. Okay, students. If a general combination of rotation and translation. Motion of a rigid body in a general, if the body is fixed at a point or along a time, it has only rotational motion. We know that force is needed to change the translational state of body. We know that force is needed. We know that force is needed to change the translational state of body to produce a linear acceleration. Okay, what is the analog force in the case of rotational motion? To look into the question in a concrete situation, example of opening or a closing of a door. A door is a rigid body passing can rotate. Body which okay, so like this. What makes the door rotate? It is clear that unless a force is applied, the door does not rotate. Okay, students. What I am saying, you understanding? No. What makes the door rotate? What makes the door rotate? It's clear that unless a force is applied by the door, does not rotate. Understanding? No. But any force does not do the job. A force applied to the hinge line cannot produce any rotational at all, whereas a force of given magnitude applied at right angles whereas a force of given magnitude applied at right angles to the door as its outer edge is most effective in producing rotation. Understanding, no, students? What I am saying, force applied to all the hinge lines cannot produce any rotation at all, whereas the force of given magnitude applied at right angles to the door at its outer edge is most effective in producing rotation. Understanding, no, what I am saying? It's not the force alone, but how and where the force is applied is important in rotational motion. Let me discuss. Okay. The rotational analog of force is moment of force. The rotational analog of force is moment of force. It is also referred as torque or couple. Rotational analog of force or moment of force is called torque or couple. Okay. We shall first define that moment of force or the special case of a single particle. Okay. We shall also relate it to a change in the state of rotational motion, angular acceleration of the body, rigid body. Okay, students. So here is the graph of the torque. Showing x-axis, y-axis, z-axis. Here is the torque applying at O, and this is a radius from O to P, and this is a force is given applying from P to r sine theta, from r sine theta to 0. Okay student, you can understand from this graph only. If a force acts on a single particle at a point P whose position with respect to the origin O is given by the position vector r, the moment of the force acting on the particle with respect to origin O defined as the vector product. So torque is equals to r into F. Understand now students? Torque is equals to r into F. R into F. So where r is the radius of the particle, so force is the force applied on the body, rigid body. So torque is equals to r into F. The moment of force is a vector quantity. The symbol tau stands for the Greek letter tau. The magnitude of the tau is equals to rf sine theta. So tau is equals to r into f into sine theta, where sine theta is a trigonometric identity. Okay students, tau is equals to tau is equals to r into f sine theta, where r stands for a radius, force stands for force applied to a rigid body. Okay, moment of force has dimensions m l square t raised to minus 2. Its dimensions are the same as those of work energy. It's however a very different physical quantity than work. Moment of force is vector, is a scalar, where work is scalar. The SI unit of moment of force is Newton meter. The SI unit of the torque is Newton meter. The magnitude of the moment of force may be written as tau is equals to r sin theta, F is equals to r perpendicular to F. R sin theta means it's 90 degree only. So we can write r perpendicular to F, or tau equal to rf sin is equals to rf sin. So is equals to theta rf, where r perpendicular stands for r sin theta is the perpendicular distance of the line action of f from the origin, and f sin theta is the component of f in the direction perpendicular to the r. Thus that tau is equals, note that if tau is equals to 0, if the total torque applied on the rigid body is equals to 0, if r is equals to 0 and f is equals to 0, or theta is equals to 0 or 180 degree. In that condition, r is equals to 0, f is equals to 0, theta is equals to 0 or 180 degree, then the torque applied on the rigid body is 0. Okay students, thus the moment of a force vanishes if either the magnitude of the force is 0 or if the line of action of the force passes through the origin. Okay, understanding the students? Then we go for next. One may note that since r into f is a vector product, properties of a vector product of two vectors apply to it. If direction of f is reversed, if the direction of f is reversed, the direction of moment of force is reversed. If the both r and f are reversed, the direction of moment of force remains the same. Since the rf is a vector product, properties of vector product of two vectors apply to it. If the direction of f is reversed, the direction of the moment of force is reversed. Okay students, if the direction of f is reversed, the direction of moment of force is reversed. If direction of both r and f are reversed, the direction of moment of force remains the same. Okay students, you are understanding now? Okay, that's all. So this is the completion of the torque, students, right? This is the completion of video. I have to end the video at this point. Okay, thank you, bye bye, let's meet again